So, okay, we'll go through the second part of today's lecture. Making sure this is recording. Yeah. All right. So, so today's lecture will look, the second part will look at embeddings, vector and semantic search with some applications in recommender systems. This kind of provides good context for mini project 1 as well. And it's anyway a nice topic to go through. And there's tons of intuition in this topic. Okay. So I think motivation is when you look at your own Netflix, page, right? And you'll see that your carousels, so each row, you can call it a carousel. Your carousels are personalized. Even popular on Netflix, like for me, is personalized to what I watch. It's popular, but among the popular ones, which ones are relevant for me? It's even personalizing by that, right? It's not giving me some random popular stuff that I may want to watch. These are kind of connected to the kind of things I've watched in the past. And then there's trending now. Again, it's kind of specialized. And then there's also genres that you'll see, like your account might be different from your friends or your spouse's account in the genres that it shows at the top, because those are the genres that are personalized to you, right? So that's the context here. So it's popular yet personalized, and the trends are personalized, the genres are personalized, and so on. So everything, every single thing on your Netflix page or account is hyper personalized. And I don't know if you guys know this, but even the image that they show you for the movie, like you might get an image thumbnail that's different from the thumbnail for me because it's personalized to me. So Netflix calls it art, personalizing the art. What is the image or thumbnail that will be attractive to you? So if there is a movie that has romance and action and someone prefers romance, you'll get a thumbnail that's more on the romantic side. And then the same movie, someone else might get a thumbnail that's more action oriented, right? So it's so that the propensity to watch or click might be higher, basically messing with your brain. But so it's hyper personalized. And back in 2008, I think, there was this Netflix $1 million prize. So Netflix hosted a competition, kind of like a Kaggle contest with leaderboards and stuff, where teams all over the country and the world were invited to train on a train set. So they would give a train set like 100K or 1 million, so that time $1 million was a big number. So now $1 million is not such a big number, but they had 1 million data points as well. So they had different data set sizes, and you could train on it, and you can also test locally on your train test split. But they had a held out test set on which you were evaluated. They would not share that with you. They would just ask you to make predictions, and then they had the ratings for it, but they would not share with you, and then they would evaluate on it. And so a leaderboard would be built out of that. And so different teams would go through different stages on the leaderboard, and as time progressed, some leaders emerged. So these guys are one of the team that won. They did a combination of algorithms like matrix factorization. So a combination of approaches is what got them the first prize. So this was a leaderboard. So team name, what is the rank, what is the score, and what is the improvement over the baseline. So Netflix had a baseline and said, okay, this is the minimum you should be getting. If you're getting less than this, then then maybe train better. So they got a 10% improvement over their own algorithm. So that's how the top the leaders got the prize, right? And yeah, I mean, your Kaggle contest is going to look like this as well. There's going to be a leaderboard, and there'll be a score and everything. So the idea, if you look at recommendation systems, there are two main approaches. One is collaborative filtering and content-based filtering. So with collaborative filtering, the idea is that you don't necessarily have to understand the movie to make a recommendation of the movie to the user. Like, the algorithm doesn't have to understand the movie at all, right? It's purely behavioral in nature. it's based on collaborating with other people who watch the same movie. Like my friend watches this movie and says, you should watch this movie. I'm like, I trust you as my friend, I'll go watch it, right? I may not even need to know what it's about. I just trust that you picked a good movie, so I'll just go with it, right? So that's collaborative filtering. There is no essentially content-based signals that are used to make recommendations or predictions for what you should watch. So as an example, let's say there's 5 movies we're looking at: Avatar, Arrival, When Harry Met Sally, Before Sunrise, and Minions. So one is like sci-fi, couple are sci-fi, adventure, 2 are in the romance, and one is like comedy, animation, right? So there's like 3 genres that you can see, or 3 or 4 genres. And let's say there are 5 users: Rishi, Michael, Karthik, Roshan, and Amy. And then there is a partial understanding of what you watched already and what you like or you don't like, right? So it's a thumbs up if you like and you watched it before, and it's a thumbs down if you didn't like it, right? But there are also gaps. For example, Michael doesn't like Avatar, but does Michael like Arrival, right? So there are these question marks. So it's like predict the missing ratings or missing likes and dislikes. And there is previously, with collaborative filtering, people used to think that you had to have explicit ratings, explicit reviews, that customers or people who watch the movies would say, yes, I liked it, I didn't like it, on a scale of 1 to 5. But then Netflix realized that it's too much to get a lot of data by asking people to leave a review with a particular rating. Rather, you can just see if they spend enough time watching a movie, that's an implicit like, or they stop watching a movie and say that's an explicit dislike, right? Because I was not so interested, I just stopped watching. So that gives you a signal. So you have implicit signals and explicit signals. So they started shifting more towards the implicit signals. So you can scale the data on which you can train. So you want to predict the question marks. That's the problem, right? And so let's say if I want to know if I like Arrival, I'm going to see that I'm kind of similar to Rishi because we both like Avatar and we both like Minions and we both don't like When Harry Met Sally. So somehow my preference is matching up with Rishi, and I can say, well, Rishi likes Arrival, so maybe I'll like Arrival. And so I can predict a like for Arrival because I kind of connect with Rishi, right? So that's collaborative filtering. In the simplest sense, with just one other user or friend, you can predict your missing ratings. And I can do the same for the other movie and say, okay, I probably dislike Before Sunrise. And I can ask the same question for Amy. Does Amy like When Harry Met Sally? Well, who's Amy similar to, right? Maybe Amy is similar to, let's see, did we say who she's similar to? Maybe Michael? I don't know. I'm not sure which, or Roshan? I don't know. Anyway, so you're similar to either Roshan or Michael, one of those. So you can keep doing that and mapping who are you most similar to and then fill in the blanks, right? And then you can fill in all the blanks, okay? So this is pure collaborative filtering. I didn't have to understand the movie. I didn't have to know any keywords for the movie. I didn't have to know who's acted in the movie, who's the director. I had no information on that, but I could still make predictions. And that's why it's called collaborative filtering. So now the key thing is that practically you're not going to depend on just one person. You're going to use information from a bunch of people to understand your type. Like you might be similar to a few people, average of few people's preferences. But the question is, who are those 4 or 5 people? And that's where the matrix completion problem comes in. And it learns, the matrix completion problem enables you to learn how you can collaborate with a few other users and learn your preferences. So everyone's like, I'm an average of 5 other people's preferences. That's the assumption, right? But who are those 5 people? They may be different for you and for me, right? That's the idea of collaborative filtering. So in matrix completion, you factor this matrix of ratings that you know and the ratings that are missing, into a user factors and a matrix movie factors, right? And the idea is that if I look at Amy, Amy has a user factor. There is some encoding of Amy's preferences in the user factor for Amy, right? And that's one row of the user factor matrix, right? And if I want to know if Amy likes Arrival, I'll go to the Arrival movie factor. So one of the columns in the second matrix, I'll extract these two and take a dot product and see if that score is high, it's likely that Amy likes Arrival, okay? And the reason this works is because, yeah. Yeah. So done naively, yes, if you make some assumptions here and there, it'll happen that way. But one thing I forgot to mention, or I was about to mention, is that you don't know the user factors and movie factors ahead of time, right? These are the parameters of the model that you're learning. So the parameters are all listed or spelled out here. The whole user factor matrix and the whole movie factor matrix is unknown before you learn. What's the data? The data are the ratings that are already present in the matrix on the left. So you can construct a loss function between the known ratings in the blue matrix and the unknown user and movie factors on the right, like let's say a quadratic function. Say, okay. And the reason dot product works is because if you look at Amy's rating on the left in blue, that's actually a dot product of Amy user factor and the Arrival user factor. That's why it works. It's just the way the matrix decomposes into two matrices and how they multiply out. You take a row of one matrix, the column of the other matrix, and that's how you get the rating in the ratings matrix, right? Because of the math, you just have to take a dot product if you know the factors right. So the question is, how do you learn the factors? And that's where the learning happens. So all the known ratings are your data. The user factors and the movie factors matrix is the unknown, and that's the parameter, and that's what you learn. This is the simplest version, right? So let's say Netflix gave me like, I think they had a 100K data set as well. So I had a 100K data set and I split into train, validation, test. I'll take that 80K or 90K data, and those are my missing ratings. Those are my known ratings. My missing ratings might be in millions, but I can still use, as long as every user and every movie has some representation in the ratings matrix, I can get a user factor and a movie factor for every single movie and every single user. That's the condition. You have to have at least one data point or one rating for every single user and every single movie in the 100K data points. And you can still predict from that 100K the missing ratings for 1 million or higher number of data points. Let's say you had 1,000 users and 1,000 movies, that's 1 million ratings in total, right? But I can just get a subset of 100K and predict for the 1 million, okay? Does it make sense? Yeah. The advanced version of this is where autoencoders came in. And so people started with a simplified matrix factorization model, and they expanded it out to autoencoders, added nonlinearity. There's no nonlinearity here. I mean, it is nonlinear in the sense that x times y is nonlinear, but there's nothing else that's nonlinear. If you fix one of the matrices on the right, the other is linear. So it's a bilinear model. It's a very simple bilinear model. So people added nonlinearity later through autoencoders. But this is one of the core models that was used to train and solve for collaborative filtering. Okay. Any questions on this, the setup? Yeah.
Is the blue matrix, the original matrix, just binary in this case? Continuous values?
So in that data set, they had ratings from 1 to 5.
I see.
Yeah. So if it's binary, you'll have to make some data changes so that you're able to learn properly. Yeah, you don't want a 0 in the rating. So you can change it to -1 or something else.
one more question. How sparse are these matrices usually?
Very sparse. I mean, they're sparse in the sense that the known data is much less than the unknown, right? So you might have 1 million ratings or 10 million ratings, and you only have access to 200K data points, 200K ratings. Okay, so if I learn the Amy, the user factors matrix and the movie factors matrix, once I learn it, then I say, does Amy like Arrival? I have no idea if Amy likes Arrival from the ratings matrix. It's missing. Does Amy like Arrival is missing in the blue matrix, but because I've learned the user factor for Amy and I've learned the movie factor for Arrival, I take a dot product and let's say it comes out high, like 0.9. That's very similar. So I say, okay, let's say cosine similarity. Yeah, cosine similarity is 0.9, very high. So I'd say very likely Amy is going to like Arrival. Let's recommend Arrival to Amy. Okay. So then you say Amy likes Arrival. Yeah. So this kind of a factorization is very similar to a very popular method in linear algebra. Any guesses on that? There's another kind of factorization of a matrix that's very popular. Yeah, it's close to eigenvalue, singular value decomposition, right? So SVD exists for every single matrix. So any matrix, whether it's complex, real, whatever, rectangular, square, has a singular value decomposition. So you take a matrix X and you decompose it into U, sigma, and V transpose. So in the previous version here, obviously you're not computing an SVD, but essentially you can say that you're mashing up U and sigma, and you're mashing up sigma and V to two factors, the user factor and movie factor. The sigma here is kind of a scaling. It has some scaling information there. But it's kind of similar to this. Okay, so every matrix has an SVD. So yeah, the unfortunate thing with SVD is that you have to have a complete matrix. But if you had a complete matrix, then you already have the ratings. Right? We have an incomplete matrix, and that's why SVD doesn't apply. Right? People have tried to fill it up with some zeros or something. Oops. Okay. This problem has happened again. All right. So every data matrix has an SVD. But yeah, we couldn't apply SVD because some ratings are missing a lot of ratings are missing in the blue matrix. Okay, so yeah, so one downside of collaborative filtering, it's already on the slide. What's the downside? Yeah, it's the cold start problem. So the cold start problem is when you have a new user that's come into the picture or a new movie, I have no idea, there's no prior history. What do I recommend? Because it doesn't fit in this model. Only if I have a known user factor and a known movie factor can I make predictions, right? So that's called the cold start problem. So that's where the other approach comes into play, which is content-based filtering. Because collaborative filtering captures behavior when you already have a history for a user or a movie. So it's good, but you have to have some history. But if it's fresh, a new movie got released or a new user came into the picture, then I don't have predictions for that. Yeah? So that's a cold start problem. So let's say I wanted to ask this question, do I like the movie Men in Black, right? So I like a lot of sci-fi movies. So that's where I'm picking these things. So let's say I watched Arrival, and then I say, would I like Men in Black? Because I'm giving you information that I've watched Arrival. Would I like Men in Black, right? So I would say, yeah, I'm likely to watch because these movies are similar in some sense. Men in Black and Arrival are similar. So that's where content-based filtering comes in, where you learn some embeddings for these movies, right? They somehow appear in similar context, or you have a learning process for embeddings as well. So you have to learn embeddings for movies and then say, when I place the learned embeddings in the same graph, do they fall close to each other or are they far away from each other? If they're close to each other, then you can take a cosine similarity or dot product and say they are similar, right? Yeah, so you can see here, if I learn the embeddings right, then the movies will be kind of spread out in this way, because one is a comedy, one is like a romantic movie, and then the others are sci-fi. So they will cluster in a different part of the space, right? Yeah, so these embeddings are typically 128 or 256 dimensions. And then the question is, how do we obtain these embeddings? Through a deep learning model. Somewhere the movies and users are interacting in some way, shape, or form, and you have to start with some raw features. Like, let's say I have a fresh movie, I have no history of it, but I'll still be able to get some features like who's the director, who are the actors, what are some keywords for the movie, which language is it, and then I might have a deep learning model that can still take those features and generate an embedding, like even without other information, right? So, so you can get an embedding through a deep learning model. And then the latent dimensions of embeddings, you can interpret as like a combination of genres. Let's say you had 128 dimensions for a movie. What do those 128 dimensions actually represent, right? Typical interpretations are based on the data. In this case, the data is for movies, so likely it's going to be a combination of genres. Like this, if you see, even Netflix says it's a romantic comedy movie with some action, or this with that. So it's kind of like mixing up genres as well, and not just giving you a straight romantic movie, right? Like it kind of like combines stuff and says, here's a new category for which I'm giving you some recommendations because I think you like it. So the hidden dimensions of these embeddings might also represent that kind of an information. You don't know ahead of time what each dimension represents, but you can, once you learn it, you can interpret it that way. Yeah? Does it make sense? Okay. So let's say you learn embeddings through a deep learning model or somehow. I want to now know, if I'm given a user and I'm given a movie, how are they similar or are they not similar, right? That's where the cosine similarity metric is one of the metrics that comes into play. So you can either take a dot product, but dot product is not normalized. So cosine similarity normalizes the vectors, and it actually captures the angle between the vectors, right? Because it's cosine of the angle. So you get the angle. So the smaller the angle, the more similar those two quantities are, right? So in this case, for example, is Men in Black similar to Arrival? Let's look at the angle, okay? If the angle is small, is cosine high for a small angle, or it's small for a small angle? It's inverse, right? Sine is high. If the angle is high, the sine is high, but cosine is actually inverse. So the larger the angle, the smaller the value of cosine. Okay, so there's an inverse relationship. So we know intuitively, looking at this image, that the smaller the angle, the more similar they are, right? The cosine would actually be large for a small angle. So you'll actually see cosine score being high. So higher the score, the more similar those two objects are, right? In contrast, let's say I want to see if Men in Black is divergent or different from the movie Harry Met Sally, then the angle, if the embeddings are learned right, the angle would be higher, and so the cosine of the angle would be smaller, right? So the cosine gives you a score, okay? So yeah, smaller angle, higher cosine similarity, lower angle, lower, yeah, smaller angle, yeah, lower angle is, smaller angle is, sorry, I said lower angle, larger angle. Larger angle is lower cosine similarity, yeah. Okay, and mathematically, cosine similarity is represented as, if you have two vectors, x and y, it's the dot product. So the dot product is x transpose y. We did a dot product question last class. But then you normalize it by the magnitude of x and magnitude of y. And magnitude is represented by How do you represent magnitude for a vector? The norm of a vector, right? So you take, let's say you use a L2 norm, it's the sum of the squares of the entries of that vector. So that's the denominator, right? You see L2 of x, you just take all the entries, square it and sum it up. That's the magnitude. And then take a square root. You can take a square root. So yeah, the same thing for y. So that kind of makes sure that cosine similarity is bounded. What is it bounded by? What's the lower bound and upper bound? -1 and 1. Yeah. You know, no matter what the angle is, the cosine of that angle has to be between -1 and +1. Yeah. Okay. So here's a question. If you identified a movie, let's say you had two movies, and somehow the angle is 90 degrees, what does that tell you about the relationship between the two movies?
They're very dissimilar.
They are dissimilar.
Yeah.
Okay. Sorry? Not related. They're orthogonal. It's like, is comedy and action related? Well, they can be, but they don't have to be. It can be completely different, right? So you can have a comedy movie without action, you can have an action movie without comedy, or you can have both. So it's like there's no real relationship. Okay. So yeah, so cosine similarity is between -1 and 1. And this is also called in math it's called the Cauchy-Schwarz inequality. Also represented this way. Yeah, and some more math. This is the Euclidean norm of x. Okay. All right, so we looked at this example of similar and dissimilar. Yeah. Yeah. So let's look at this example. So we looked at embeddings of movies in the same space. You can also embed users in the same space. So this is the same idea as the user movie factors. They can be in the same space for comparison, right? So not just movies, I can also embed users. And then I can ask the question, do I like this movie? Do I like that movie? Like for example, I can like Men in Black as much as I like Harry Met Sally, although Harry Met Sally and Men in Black are orthogonal. They're not so related. They're different genres. But I as a user can like both of them because I fall right in the middle. Yeah. So when you embed users in the same space as movies, you can also make comparisons between users and movies and say that I like both the movies because I like rom-coms, I like a mix of genres, so you can have that combination as well. Okay. What if you like all kinds of movies? Yeah, you'd probably be equally far away from where you might be at the origin. You might be kind of like in the center of the circle, right? Like a zero vector. All your vectors are normalized, you're right in the middle. So anything you take a dot product is 0. So you should get the same answer for every single movie. So it'll be a 0. Yeah. Okay. So let's do an exercise just to get the math of it down. So let's say that Avatar had a 4-dimensional embedding. It's already computed. And then Michael, the user, had an embedding as follows. So the question is, should we recommend Avatar to Michael? Yeah. So just go through use the cosine similarity, compute the cosine similarity or estimate the cosine similarity to see if you want to recommend Avatar to Michael. No? Yes? No? How many no? How many yes? How many I don't know? We don't have I don't know, so it's either a no or yes. So what's the idea? How do you say it's yes or no? What are you going to look at? Numerator is negative, yes. Right. That's definitely like pretty orthogonal. So yeah, I think the negativity is an interesting thing on how you interpret when the value is negative. Like you can have two vectors that are in the same plane. It's just one is opposite of the other. So do you call it completely dissimilar? Like I hate this, or I just don't want, I hate it. So is that a negative? And then if that's the case, if that's how it's set up in the embeddings, then it works, right? So we just have to examine that that's the case. Like if someone really hates a movie or hates a genre, then that's actually a -1 on the cosine similarity. If that's the case, then I have some distaste for these kind of movies, right? Because the dot product is negative. Okay. Sometimes the embeddings are such that you have to look at the magnitude versus the sign. If that's the case, then you see if the magnitude is between 0 and 1, and is it closer to 1 or is it closer to 0, right? In this case, even if you looked at the magnitude, it's less than 0.5, right? So you can say that it's going to be dissimilar either way with respect to magnitude or with respect to the direction, the sign. Yeah. So I would not recommend Avatar to Michael. Okay. So you can replace movies with words and this still works, right? I can have different kinds of objects here, and then you can have embeddings in that space as well. And I can also embed sentences and not just words. How do I get a sentence embedding from a word embedding? So let's say I had a sentence, I love to drive cars and paint flowers too. I only have word embeddings. Yeah, just average it. Averaging is a simple way. And then there is like a technique called TF-IDF averaging, where you look at how important is that word for averaging and use the importance to actually average. It's kind of like paying attention. So TF-IDF based averaging for sentence embedding is like paying attention to the words. Like are they filler words? Like if you want to average the or a or to, I think you can just skip those words, right? You actually want to look at the words that actually matter. So that's what TF-IDF will help you with. So that's another way of doing it. You can capture a average of the embedding. When we look at BERT models, you don't just average word embeddings, you actually pass the whole sentence through BERT, and then you can extract certain tokens like the start token, or you can also average the tokens at the last layer, and that gives you a sentence embedding. So averaging is like a little bit of a linear operation, which doesn't really capture correlations between words very well. So, but you can still do that, that's a start. When we look at BERT, I think for mini project 1 we have like BERT based embeddings, then you can get to play around with it. I think we have a demo, I think you'll have a web demo as well, where you can compare, you can type in sentences and see which categories is it closer to, and that'll be a nonlinear embedding, right? Nonlinear computation of the sentence embedding. Okay. All right. Yeah, for a deep learning model, we usually look at the last but one hidden layer of activations, and that gives you the embedding. So you pass through a deep learning model, just look at the last but one layer, and that gives you embedding. So yeah, I think for your mini project 1, you look at sentence BERT as a way to get sentence embeddings. Yeah, we might look at a baseline embedding as well, like love embeddings or simple averaging of words for embeddings as well. Okay, what's the time? 6:24. All right. I think the next lecture we'll look at a demo and semantic search. So you can type in different sentences and see which categories are highlighted for that sentence, right? So we'll look at a demo on that, and you can also implement a demo like that yourself in mini project 1. Okay, so it's semantic search. Like, I mean, the traditional search is kind of very limiting. It really doesn't understand the meaning of the words as much. Like if you look at traditional Google search or whatever, before it used to be based on like frequency or how often do you see these things correlated. You don't have to really understand what that is asking. And with traditional search, if you ask very complex queries that it hasn't seen before, it'll fail. There'll be no result. But with semantic search, you can phrase things in a different way and search, but it'll understand the semantics and map it back to the results that, that make sense. So that's kind of the power of semantic search. Yeah, I think we spoke about this in the first class. If you ask this question, king minus man plus woman, it wouldn't have made sense before embeddings came into play. How do you subtract words and add words? That doesn't even make sense. But if you had embeddings, you subtract embeddings and add embeddings, and then you do cosine similarity with other words embeddings to see which one makes sense. So for example, you can actually, we'll probably have this in, I don't know if we'll have this in the mini project, but if you take the embedding of king, man, and woman, you subtract and add, and you search across all the words that it's close to, very likely queen will come up at the top, right? You subtract the man and you add the woman, that makes sense, that's queen, right? You just swap the gender. But mathematically it'll also show up, because when you do that addition and subtraction and you do a cosine similarity search, queen will rank at the top 5, right? You'll also have other words, but queen will be at the top as being similar to king. Yeah. Okay. So yeah, I think we'll stop here. We'll look at a demo on semantic search in the next lecture on Monday. So that'll be on Zoom, and then we'll move on to transformers as the next topic. Okay. If you have any questions, you can just stop by here, or we'll see you on Monday.